Hi, I'm Xiaodong Yang. I'm a PhD student from Vanderbilt University. My advisor is Professor Tyler Johnson. In this presentation, I will give a talk about our work on the reachability analysis of deep ReLU neural networks using Facet-Vertex incidence. This work is done with the help from my colleague Tran from the University of Nebraska, as well as my colleagues from Toyota Research Institute during my internship. In this presentation, we will first introduce the reachability analysis and its related works, and then we will talk about the preliminaries of Facet-Vertex incidence matrix, and based on that, we propose a new set representation. With this set representation, we propose a method for the reachability analysis of neural networks. And also, we propose another algorithm called backtracking algorithm, which aims to identify all the unsafe domain. Finally, we evaluate our method on different benchmarks. The reachability analysis is about given a neural network and input domain, we can compute or search its output reachable domain. The main challenges for the ReLU neural network is that the ReLU activation function has two different linearities over the X input range. When a neural network has n neurons, there will be at most 2 to the power n combinations of linearities. There are two categories of methods for the reachability analysis. They are over approximation methods and exact analysis method. In this work, we will talk about the related works. First of all, I will introduce soundness and completeness in the verification problems of neural networks. The soundness means when the solvers return safe, the neural network is actually safe. The completeness means when the solvers return unsafe, the neural network is actually unsafe. For over-approximation methods, they are sound but not complete, which means they can determine the neural network is safe, but they cannot determine the neural network is unsafe. Here we mainly present one category of the over-approximation method, which is ReLU over-approximation. There are works like zonotopes, abstract domain, and linearization. In these works, instead of considering the two different linearities in the ReLU function, they use one set or domain to over-approximate the ReLU function, as shown in these figures. Here, the blue lines represent the actual ReLU function, and the red area represents the set or domain for the over-approximation. These methods are efficient because they can simplify the reachable set computation, but the output reachable domain is conservative because the over-approximation errors is exponentially accumulated with respect to each neuron. For the exact analysis methods, they are sound and complete, which means they can determine the neural network is safe or unsafe. Here we present four categories of the exact analysis methods. The first one is the satisfiability modulo theory based. There are works like ReLPlux and Marble. In these works, they encode the whole neural network using the SMT solver and then deals with high-dimensional LP problems. The second category is the mixed integer linear program based. There are work like Venus. In this work, they encode the whole neural network using the mixed integer linear program, and then similarly deals with the high-dimensional LP problems. The third category is a symbolic interval method, which is an over-approximation method. There are works like ReLU and Neurify. The symbolic interval method computes the symbolic bounds of neural networks by considering the dependency between nodes. The main strategy of the ReLU and the Neurify is that in each iteration, they refine the over-approximation and then compute a tighter reachable domain. The iteration will be repeated until they found the neural network is safe or they found any counterexamples. But when the approximation is too conservative, it may require many iterations. The first category is a set-based method. There are works like polytope-based method and star set. Normally, there are two set representations for the convex set of convex polytopes. They are H representation, which is a set of facets, or V representation, which is a set of the vertices. For the polytope-based method, they use both of those set representation in the reachable set computation. But there are frequent conversion between the H and V representations, which are not very efficient. To solve this problem, they also propose another method called star set, which is H representation-based method. This method can avoid the conversion between H and V representation such that they can improve the efficiency. But still, there is a lot of LP problems involved in the computation. Overall, to improve the computational efficiency, we proposed our method, which is based on the Facet-Vertex incidence matrix. Our method can compute the exact reachable set without any LP problems, such that we can improve the computational efficiency. In that section, we will introduce the Facet-Vertex incidence matrix. Its definition is as follows. Given a four-dimensional convex polytope P in D dimension, the Facet-Vertex incidence matrix is a matrix where an entry 1 indicates that the facet F contains the vertex V, and the entry 0 indicates it does not. Here is an example of a three-dimensional cube. This cube contains 6 facets and 8 vertices. And the Facet-Vertex incidence matrix here essentially describes the containment between the facets and the vertices. For example, we have a facet F1 in this blue area. It contains vertices like V1, V2, V3, and V4. You can see their corresponding entries are all 1 here. Based on this F matrix, we can propose a new set representation, which consists of the F matrix and also the values of the vertices. With the new set representation, here we present the operations needed for the reachable set computation of neural networks. The first one is affine transformation. We denote it as function T. The affine transformation actually only changes the value of vertices, and the F matrix will remain the same, as described in these equations. The second operation is division by a hyperplane. Here we illustrate this process with an example. We have a three-dimensional cube P and a hyperplane H. The F matrix of the cube P is described in this graph in blue blocks. The blue line between them describes the containment. When the intersection between H and P happens, it generates new facet 7 and new vertices 9, 10, 11, and 12. When division happens, the QP will be split into two subsets by the hyperplane H. Correspondingly, for each subset, the original F matrix will keep all the facet and vertex of this subset and discard others, such that it can form the final F matrix for this subset. After the introduction of the new set representation and its operations, here we present our method for the reachability analysis of neural networks. First, we start with the reachable set computation of one layer, and we denote this process as function L. We assume that one layer includes a fine transformation, then the process with each neuron, And we demonstrate those two processes using an example of one layer with two neurons and an input set P. For affine transformation, as we introduced in the previous slides, it only changes the value of vertices and the F matrix will remain the same. So this process is demonstrated in this figure. The P will be affine transformed by the weights and bias into a new set P dash. Here the X1 corresponds to neuron 1 and X2 corresponds to neuron 2. After the affine transformation, we talk about the process with each neuron. Here, we denote the process in the neuron I as function Ri. The function Ri takes in set and output set. It essentially maps all the negative xi dimension in the set to 0. Here is the details of this process. When the function Ri takes in the set P dash, for all the element points x in the set P dash, if its xi dimension is negative, then the xi dimension will be set to 0. When there are multiple neurons processed, for example, Ri and Rj, the order of considering each function won't affect the result. Both of those two processes will set all the negative xi and xj to 0. Here, we demonstrate the process with an example. We have two neurons, neuron 1 and neuron 2. X1 corresponds to neuron 1, X2 corresponds to neuron 2. The function R1 describes the process in the neuron 1. The function R2 describes the process in neuron 2. After the application of functions R1 and R2 on the set P dash, all the negative xi and x1 and x2 dimension will be set to 0. Finally, we have the output domain in this blue area. Here, we talk about the application of function R1 and R2 on the set P dash. First of all is the function R1, which corresponds to the process in neuron 1. Recall that there are two different linearities in the ReLU activation function. Here, the hyperplane H1, which is x1 equals 0, is actually the boundary between those two different linearities in the neuron 1. So we use this hyperplane H1 to conduct the division operation on the P dash. Then the P dash will be split into two subsets, P1 and P2. P1 contains all the positive x1, P2 contains all the negative x1. Then the P2 will be projected on the hyperplane H1 by setting all the negative x1 to 0. Here, the P2 will generate P3. Those two procedures describe the function R1, which takes in the set P dash and generates P1 and P3. P1 and P3 will be the input set to the function R2. The procedures in this process are the same. Here we have the hyperplane H2, which is x2 equals 0. We use this hyperplane to conduct the division operation on the input set P1 and P3, and then generate the set P4, P5, P6, P7. For all the set that contains a negative x2, they will be projected on the hyperplane H2 by setting all the negative x2 to 0. Here we generate the new sets P5, P6, P9, and P8. They are the output of this neuron and also the final output of the application of R1 and R2 as described in this figure. Here is a summary for our reachability analysis method from previous slides. Recall that we denote the reachable set computation of one layer as function L. The process in one layer includes the fine transformation on the input set P, and then the process with neurons Ri. Based on the function T and R, we formulate the computation of one layer in equation 2. Based on the equation 2, we can compute the reachable set of neural networks layer by layer as described in this equation 3. When a neural network has n neurons, the maximum number of reachable set will be 2 to the power n. In that section, we will present our backtracking algorithm, which aims to identify all the unsafe input domain of a neural network, and then we can use them to train a safer neural network. The definition is here. Given an input domain I, the reachable domain of a neural network will be the union of all the reachable set we computed with our reachability analysis method. When the reachable domain O overlapped with the unsafe domain, the backtracking algorithm can compute all the unsafe subspace in the input domain that generates the overlapped unsafe domain. To realize the backtracking algorithm, we need to do some modifications of the set representation as well as its operations. First of all, we modify the set representations by adding two more items, M and D. M and D basically describe an affine transformation. With M and D, the new set representation essentially encodes a affine transformation between the current set P and another set P0. With new set representation, we have the new affine transformation T. Previously, the affine transformation will directly apply on the values of vertices. With the new set representation, the affine transformation will directly apply on M and D, such that F0 and V0 will remain unchanged. For the division operation, let's say we have a hyperplane AX plus T equals 0 on the set P. With the new set representation, this hyperplane H will be mapped through the affine transformation into a new hyperplane H dash. And this H dash will be used to do the division operation on the set P0. So that is all the modifications we need to do for the backtracking algorithm. Here we demonstrate the backtracking algorithm with an example. Let's say we have one reachable set that computed with the new set representation. As you can see, F0, V0 are essentially describing the input set P0 in the input domain, and M and D are the affine transformation between the P and the P0. So when there is an unsafe domain characterized by the hyperplane H, we can map the H through the affine transformation M and D into the input space and generate a new hyperplane H dash. And then we can use this hyperplane H dash to do the division operation on the P0 and identify the unsafe domain in the input space. In the previous slides, we introduced the Facet-Vertex incidence matrix and the set representation. We also present our methods. One is for the reachability analysis of neural networks, and the other one is a backtracking algorithm which aims to identify all the unsafe domain of our neural network. In the next section, we will evaluate our methods on different benchmarks. Here, we evaluate our method with some safety verification of neural networks. The benchmarks are the neural network controllers for the airborne collision system, which is proposed by a group in Stanford University. The controller consists of 45 neural networks. Each neural network has 300 ReLU neurons. There are 5 inputs. There are rho, theta, psi, v on, v int. Rho is the distance between the on-chip and the intruder. Theta is the relative angle between the heading direction of on-chip and the intruder. The psi is the relative angle between the heading direction of the on-chip and the heading direction of the intruder. The V-on is the velocity of the on-chip. The V-int is the velocity of the intruder. The output of the neural networks correspond to the scores of 5 actions. The 5 actions are clear of conflict, weak right, weak left, and strong left. There are 10 properties for the neural networks controllers. Each property specifies one scenario with input constraint and an unsafe output domain. The properties 1 to 4 are designed for all 45 neural networks, and the property 5 to 10 are only for some specific neural network controllers. First, we evaluate our method with the safety verification of properties 1 to 4 on all the 45 neural networks. Totally, we have 180 instances here. We also compare our methods to the other related works. It includes the exact analysis method and over-approximation method. The exact analysis method includes the NeuroFi, which is a symbolic interval-based, Marble, which is SMT solver-based, the two method which are star set based, and also the Venus, which is based on the mixed integer linear program. And we also include one over approximation method from the Iran tool. Here we plot the running time of each instance in the cactus plot. The x-axis represents the number of instances verified, and the y-axis represents the running time. As you can see, our method is much faster than other methods, and our method is the only one that can verify each instance within 2 minutes. You can also notice that our method is in some cases is slower than the NeuroFi, but when we run the verification without a timeout, you can notice that in some cases the NeuroFi method can take thousands of times, and in the worst case, our method is slower by like around 2 seconds. In the best case, our method is faster by like over 3,000 seconds. So overall, our method has much higher computational efficiency than the other method in the verification of property 1 to 4. Next, we evaluate our method with the verification of properties 5 to 10 on their target neural networks. The timeout for this verification is set to 1 hour. The result is shown in this table. P here represents the property, the net here represents the target neural network. The result shows the verification result, and the rest represent the running time of each method. As you can see, our method is faster than other methods in most of cases, and also our method can correctly verify all the results here. Overall, the results show that our method has higher computational efficiency than the other related works in the verification of properties 5 to 10. In this presentation, we first introduce the Facet-Vertex incidence matrix. Based on this matrix, we present a new set representation and the 2 operations on it. With this new set representation, we propose our method for the reachability analysis of ReLU neural networks. Our method can compute the exact output reachable set of the neural networks layer by layer. We also propose another algorithm called backtracking, which aims to identify all the unsafe input domain of neural networks. To realize this algorithm, we did some modifications to the set representation as well as its 2 basic operations. Finally, we evaluate our method with different benchmarks, and the experimental results show that our method has much higher efficiency than the other related works. For the future work, we are planning to apply our reachability analysis method and the backtracking algorithm into the training process of neural networks, such that we can identify all the unsafe domain of current neural network candidate, and then feedback them into the next training process, such that we can have a safer neural network.